This is AP Psychology, Chapter 6 on Perception. Perception involves the selection, organization, and interpretation of sensory information. It quickly becomes one of psychology's primary concerns as early researchers attempted to explain illusions. In organizing sensory data into a whole, perception, our first task is to discriminate figure from ground. We then organize the figure into meaningful form by following certain rules for grouping stimuli. We transform two-dimensional retinal images into three-dimensional perceptions by using binocular cues as retinal disparity and monocular cues such as relative size of objects. Our brain computes motion as objects move across the retina. A quick succession of images can also create an illusion of movement. The perceptual constancies enable us to perceive objects as enduring in shape, size, and lightness, regardless of viewing angle, distance, and illumination. The consistencies explain several well-known illusions. Studies of sensory deprivation reveal that for many species, infancy is a critical period during which experience must activate the brain's innate visual mechanisms. For example, when cataracts are removed from adults who have been blind from birth, they can distinguish figure and ground and can perceive color, but they are unable to distinguish shapes and forms. At the same time, human vision is remarkably adaptable. Given glasses that turn the world upside down, people manage to adapt and move about with ease. Clear evidence that perception is influenced by our experience comes from many demonstrations of perceptual set and context effects. Because perceptions vary, they may not be where the designer of the machine assumes. Human factors psychologists study how people perceive the use machines and how machines in the physical environment can be better suited to that use. Although parapsychologists have tried to document ESP, most research psychologists remain skeptical, particularly because the results of the experiments have not been reproducible. Perception is the process of selecting, organizing, and interpreting sensory information, which enables us to recognize meaningful objects and events. Perceptions about objects change from moment to moment. We can perceive different forms of the Necker cube. However, we can only pay attention to one aspect of the object at a time. Inattentional blindness refers to the inability to see objects or a person in our midst. Simons and Chabry in 1999 showed that half of the observers failed to see the gorilla suited as assistant in the ball passing game. Selective attention means that at any moment of awareness focuses on only limited aspect of all that we are capable of experiencing. For example, even if the stimulus figure can evoke more than one perception, we consciously experience only one at a time. The cocktail party effect provides another example of selective attention. The ability to attend to one voice among many enables us to converse coherently in the midst of auditory chaos. Selective attention also limits our perception as many of an inattentional blindness. Forms of this include change blindness, which change, deafness, and choice blindness. Change blindness is a form of inattentional blindness in which 2/3 of individuals give directions fail to notice the change of the individual asking for the directions. Perceptual illusions provide good examples in understanding how perception is organized. Studying faulty perception is important as studying other perceptual phenomena. So on these lines, we can see that segment A, B, and B, C, most will think that BC is the longer segment. However, AB is actually longer than BC. Both the theoretical and practical importance of selective attention is apparent in the research on inattentional blindness. Turning into a parking lot, a driver fails to see a bicyclist riding down the sidewalk. The driver only hears a thud and first sees the bicyclist on the ground near her left front fender. A nurse locates a vial, reads the label, fills the syringe, and injects the patient. The patient receives the wrong medication and dies. A submarine commander sees no ships through his periscope, surfaces, and hears the clank of a ship hitting his deck. The ship overturns, killing 9 people on board. An airplane pilot and his crew see a light flashing on their control panel. They become so concerned with its possible cause they do not notice the plane approach the ground or even hear the alarm. The subsequent crash kills 100 people. These are all real events. Intuitively, we think that as long as our eyes are open, we are seeing. Research beginning with Ulrich Nesser's basketball study, which is cited in the text, has clearly indicated that visual perception is not like a videotape. We see very little when we're not paying attention. In Nesser's experiment, viewers who were attending the basketball tosses usually failed to see an umbrella-toting woman sauntering across the screen. Harvard psychologists Daniel Simons and Christopher Chabry replicated and extended Nesser's finding. In a dramatic demonstration of inattentional blindness, a person wearing a gorilla suit walked into the middle of a basketball game, stopped to face the camera, thumped his chest, and then walked off screen. And although the gorilla spent 9 seconds on the screen, half of Simon Chabry's research participants failed to notice the researchers' findings. The researchers' findings suggested that inattentional blindness may depend on the similarity between unexpected and attended objects. For example, they found that participants were more likely to notice the gorilla whose fur was black when they were attending to the basketball game in black shirts than when they were attending to the team in white shirts. Stephen Most, a graduate student working for Simons and Chabry, and Brian Scholl, replicated the similarity effect in experiments using stimuli presented on computer displays instead of a basketball game. The research team also found that about 1/3 of participants exhibit inattentional blindness, even to objects that are distinctive in color, shape, or path and motion. In one study, researchers presented white and black circles and squares moving against a gray background. The participants were instructed to attend to either white or black objects. After several trials, a red cross unexpectedly appeared and moved across the computer screen. Although the cross appeared for 5 seconds, 1/3 of participants missed it. Simons concludes that at any given time, people may attend to only certain perceptual dimensions as brightness or shape. Some psychologists question whether inattentional blindness reflects a failure of perception or represents inattentional amnesia, that is, a limitation in memory. For example, Jeremy Wolf, a Harvard University medical school, suggests that people may consciously perceive unattended objects but quickly forget them. For example, research has indicated that unattended patterns of dots influence how people perceive objects in which they are attending. These results may indicate that attention is critical not for engaging perceptual processing, but rather for encoding the products of those processes in short-term memory. Simons is skeptical of this explanation. How could people notice but quickly forget such salient objects as women carrying umbrellas or chest-thumping gorillas? Instead, he suggests the alternative finding may illustrate the role that unconscious processes play in perception. Clearly, we consciously see far less of our world than we think we do. We might encode much of our visual world without awareness. Evidence from Aaron Mack's inattentional blindness studies involving primates suggests that this may be the case. In this research, observers in the experimental group are exposed to a word while those in the control group are not. Then the initial few letters of the unseen word are presented to all observers, who are asked to complete the string of letters with one or two English words. Members of the experimental group complete the string with the unseen word more frequently than do control group members, providing evidence an experimental group implicitly perceived and encoded the word. Daniel Simons and Michael Ambider provide an excellent review of the phenomenon known as change blindness, in which people fail to notice large changes to the visual scene. In the 1990s, Ronald Reidensnick and his colleagues developed the flicker test to study change detection. In this task, an original image had modified image alternate repeatedly separated by a brief blank displays. Until observers find the change, the flicker task contributed to interest in change blindness because it allowed the audience at talks or in classes to experience the phenomenon themselves. Significant changes can go unnoticed for many seconds. For example, the appearance and disappearance of a building in the background may go unnoticed. Simons and Ambinder indicate that change blindness literature has converged on the core set of findings. First, change blindness occurs whenever attention is diverted from the changed objects. Second, changes to the objects that are central to the meaning of the scene or changes to visually distinctive objects are detected more readily than are other changes. Third, attention may be necessary for change detection, with changes to unattended objects going unnoticed. Finally, and perhaps most interestingly, attention to a changing object may not be sufficient for change detection. This is demonstrated by the fact that observers frequently fail to detect changes to the central actors in motion pictures and to real-world conversation partners, even though they are paying attention to these people. Change detection may therefore require observers to encode the changes, features before and after the change, and then compare them. The reviewers note that more research is needed to determine what draws attention to some scene elements and not to others. In change detection tests, distinctiveness of specific features or explanations about a scene may be important. Individual differences of observers also need study. For example, experts in American football are better able to detect meaningful changes to football scenes than are those who are unfamiliar with the sport. Expertise seems to guide and focus the attention and indicates that some differences in change detection ability can be attributed to knowledge of the observer rather than the image properties. Research findings indicate that observers sometimes recognize a previously attended object on a memory task even when they have failed to notice the change to that object. In fact, that they even recognize both pre-change and post-change object at better than chance levels, despite the failure to detect change. Researchers are also testing whether changes are ever detected implicitly, that is, in the absence of conscious awareness of the change. For example, can observers guess the change location even if they report no awareness of anything changing, or will their performance show evidence of change detection? For example, slowed responses in the presence of change. Although Mack's review, Inattentional Blindness, suggests that this may be the case, Simon and Ambinder believe that the evidence for implicit change detection has been mixed. This research has impractical implications. People vastly overestimate the ability to detect change in their environment. We might assume that driving an automobile, we would automatically notice a pedestrian stepping into the street. The widespread use of cell phones in attention-demanding tasks demonstrates the extent of this assumption. Even admitting that the cell phone conversations require attention, we may mistakenly believe that we would automatically notice any important change in our studies of change blindness indicate otherwise. So illusions provide good examples in understanding how perception is organized. Studying faulty perception is as important as studying other perceptual phenomena. When you compare segments AB and BC, most people will assume BC is longer, but because of the angles of AB is actually longer. If you'd like to prove this to yourself, you should pause this audio or the video and measure them for yourself, and you'll see that AB is actually longer. In this picture, the vertical dimension of the arch looks longer than the horizontal dimension. However, both are equal. And so if you look at this, and you can break out your ruler once again and make the measurements, and you'll see that they are actually the same. Illusions mislead us by playing on the ways we typically organize and interpret our sensations and understanding. Illusions provide valuable clues to the ordinary mechanisms of perception. For example, several well-known illusions are based in perceived relationship between size and distance, which is generally valid. Others reflect group principles and assumptions made about the relationship between light and shadow. As visual illusions indicate, among our senses, vision is dominant. When there is a conflict between vision and other sensations, vision usually dominates a phenomenon called visual capture. Hearing captures touch. So if you see here on this illusion, the figure on the right gives the illusion of a blue hazy worm when it's nothing else but blue lines identical to the figure on the left. It gives that, but it does give that illusion that the blue runs consistently. This one takes a great deal of effort to perceive this figure. You can actually see this as a 3D illusion, and if you try really hard, you can make it seem flat, though it's very difficult to do. When vision competes with our other senses, vision usually wins. This is a phenomenon called visual capture. However, how do we form meaningful perceptions from sensory information? We organize it. Gestalt psychologists showed that a figure formed a whole different than its surrounding. Gestalt psychologists describe principles by which we organize our sensations into perceptions. They provide many compelling demonstrations of how, given a cluster of sensations, the human perceiver organized them into a gestalt, a German word meaning a form or whole. They further demonstrated that the whole may differ from the sum of its parts. Clearly, our brains do more than merely register information about the world. We are always filtering sensory information and inferring perceptions in ways that make sense to us. Organization of the visual field into objects, figures that stand out from the surrounding ground. And so here with this, you can see that it appears like men walking down steps, or arrows, or fives. So there are several different things. And it becomes difficult to see one while looking at the other. Groupings. After distinguishing the figure from the ground, our perception needs to organize the figure into meaningful form using group rules. So we will quickly observe these things and see them either by their proximity, their similarity, their continuity, or their connectedness. A discussion of visual agnosia, defined by Stanley Coren and his colleagues as a syndrome in which all parts of the visual field are seen, but the objects are seen without meaning, provides an excellent perceptual organization and interpretation task. Oliver Sacks, the opening tale in The Man Who Mistook His Wife for a Hat, provides the interesting case study of Dr. P, a distinguished musician teacher who could see but not recognize familiar faces. Likewise, he saw faces Likewise, faces where there were none. For example, patting the heads of parking meters and addressing carved knobs on furniture. When Dr. P was examined and asked to describe the pictures in a National Geographic magazine, his eyes would dart across the page, picking up only tiny details. A striking color or shape might catch his attention and elicit comment, but in no case did he perceive the scene as a whole. After his examination, the patient looked around for his hat. He reached out, took hold of his wife's head, and tried to lift it up and put it on. He had mistaken his wife for a hat. Corin describes several other forms of agnosia, including the following. A visual object agnosia people have no damage to the visual apparatus, are unable to recognize familiar objects. For example, one patient given a line drawing of a pair of eyeglasses admitted confusion and started to guess. There's a circle and another circle, a crossbar, why it must be a bicycle. Such patients also have trouble separating the parts of a figure from their overall context. Shown a picture of a clock, they may identify it. However, if the clock is crossed out with a couple of straight lines, recognition is lost. In simulagnosia, the individual cannot pay attention to more than one stimulus at a time. For example, the person may not be able to place a dot inside a circle because that would require paying attention to both the dot and the circle simultaneously. Visual object agnosia and simultaneagnosia often appear in the same patients, and disorders are sometimes grouped together as visual integrative agnosia. Another agnosia effects are more general and may involve more than one sense. People with these problems may be just impaired using, say, their tactile or kinesthetic sense as with their visual sense. For example, those suffering from spatial agnosia have difficulty negotiating their way through the world. Even in familiar settings, they make wrong turns. They become lost in their homes. Strangely, such patients also often show a tendency to ignore one side of an object in space. So when asked to draw symmetrically objects, they produce an imperfection on one side. Agnosia seems to be the result of physiological damage typical to the higher brain centers involved in the interpretation of stimuli. Although the damaged areas may be quite specific, they are not primary receiving areas of the cortex. For example, the visual agnosia are often associated with the damage to the more forward portions of the occipital cortex, which are secondary visual areas to the temporal lobes, which are tertiary visual processing areas associated with complex visual analysis. So our first task of perception is to perceive any object called the figure as distinct from its surroundings, called the ground. We also organize the figure into a meaningful form. Gestalt principles for grouping that describes this process include proximity. We group nearby figures together. Similarity, we group similar figures together. Continuity, we perceive smooth and continuous patterns rather than discontinuous ones. Connectedness, we perceive spots or areas as single unit, uniform, and are linked. And closure, we fill the gaps to create a whole object. Depth perception is the ability to see objects in 3 dimensions. Although the images that strike the eye are 2-dimensional, it enables us to judge distance. Research on the visual cliff, a miniature cliff with a drop-off covered by sturdy glass, reveals the depth perception is in part innate. Many species perceive the world in 3 dimensions at or very soon after birth. Although grouping principles usually help us construct reality, they may occasionally lead us astray. Depth perception enables us to judge distance. In the study done by Gibson and Walk in 1960 suggests that human infants reach crawling age have depth perception. Even newborn animals show depth perception. Retinal disparity images from the two eyes differ. Try looking at your two index fingers when pointing them towards each other, half an inch apart and about 5 inches directly in front of your eyes. You will see a finger sausage as shown in the inset. Binocular cues require information from both eyes. In the retinal disparity cue, the brain computes the relative distance of an object by comparing the slightly different images on the objects cast on our two retinas. The greater difference, the greater the distance. In convergence cues, the brain calculates the degree of neuromuscular strain when our two eyes turn inward to look at a nearby object. The greater strain, the closer the object. So convergence is this neuromuscular cue when two eyes move inward towards the nose to see nearer objects and outward away from the nose to see far away objects. Monocular cues enable us to judge depth using information from only one eye. The monocular cues include relative size. The smaller image of two objects of the same size appears more distant. Interposition, nearby objects partially obstruct our view of more distant objects. Relative clarity, hazier objects appear more distant. Texture gradient, a gradual change to a less distinct texture, suggests increasing distance. Relative height, higher objects are farther away. Relative motion or motion parallax, as we move, objects at different distances change their relative positions in our visual image, with those closest moving most. Linear perspective, the convergence of parallel lines indicates greater distance in light and shadow. Dimmer objects seem more distant. Artists use more monocular cues to portray depth on a flat canvas. Interposition, objects that occlude or block other objects tend to be perceived as closer. Relative clarity, because the light and distance objects passes through more light than closer objects, we perceive hazy objects to be farther away than those objects that appear sharp and clear. So as you can see in the morning fog, these look distant. And then when we, in the clear from the same position, we see how much closer they are. And this helps explain why automobile accidents happen in poor weather. Many of the times people are misjudging the distance. Texture gradient is indistinct fine texture signals an increasing distance. The harder it is to see the texture, the less likely we are to think it's close by. Relative height, we perceive objects that are higher in our own field of vision to be farther away than those that are lower. Relative motion, objects closer to a fixation point move faster and in the opposing direction to those objects that are farther away from a fixation point, moving slower in the same direction. Linear perspective, parallel lines such as railroad tracks appear to converge in the distance. The more the lines converge, the greater the perceived distance. Light and shadow, nearby objects reflect more light into our eyes than more distant objects. Given two identical objects, the dimmer one appears to be farther away. Motion perception, objects traveling towards us grow in size, those moving away shrink in size. The same is true when the observer moves to or from an object. The phi phenomenon, when lights flash at a certain speed, they tend to present illusions of motion. Neon signs use this principle to create motion perception. Our basic assumption is that shrinking objects are retreating and enlarging objects are approaching. The brain will also interpret a rapid series of slightly varying images as continuous movement, a phenomenon called the subtropic movement. By flashing 24 still pictures a second, a motion picture creates a perceived movement. The phi phenomenon, another illusion of movement, is created when two or more adjacent lights blink on and off in succession. Lighted signs exploit the effect of with succession of lights that create the impression of, say, a moving arrow. Perceptual constancy is necessary to recognize an object, enables us to see an object as unchanging, having consistent lightness, color, and shape and size, even as the illumination and retinal images change. Perceiving objects as unchanging, even as illumination and retinal images change. Perceptual constancies include constancies of shape and size, such as when a door opens. Stable size perception amid changing size of stimuli. Shape constancy is our ability to perceive familiar objects. For example, an opening door is unchanging in shape, and size constancy is perceiving objects as unchanging in size despite the changing images they cast on our retinas. Given the perceived distance of an object, we instantly unconsciously infer the object's size. The perceived relationship between the distance and size is generally valid, but under special circumstances can lead us astray. For example, one reason for the moon illusion is that cues to objects, distances, and horizon make the moon behind them seem farther away. Thus, the moon on the horizon seems larger. Similarly, lines in the Mueller-Lyer illusion may be interpreted as varying in distance from us and thus are perceived to be different lengths. Finally, in the distorted room illusion, we perceive both corners as being the same distance. Thus, anything in the near corners appears disproportionately large compared to anything in the far corners. Size and distance. The distant monster below left in the top right, red bar below right, appear bigger because of distance cues, but in actuality they are all the same size. And if you want to take your ruler to measure these, you can pause the audio or the video. Size and distance. Both girls in the room are similar height, however we perceive them to be different heights as they stand in the room's two corners of the room. And this is a unique thing called the Ames Room that gives you this illusion of size changing right before your eyes. The Ames Room is designed this way to demonstrate the size-distance illusion. Lightness constancy, the color and brightness of the square A and B are the same. Lightness constancy enables us to perceive an object as having a constant lightness even when the light falls on it changes. Perceived lightness depends on a relative luminance. Color constancy is our ability to perceive color of an object as unchanging even when its illumination changes. For both constancies, the brain perceives the quality of lightness or color relative to the surrounding objects. Perceiving familiar objects as having consistent color even when changing illumination filters the light reflected by the object. So this is color constancy, and as we can see, the color of the object appears to change. Immanuel Kant maintained that knowledge comes from inborn ways organizing sensory experiences. John Locke argued that we learn to perceive the world through our experiences. How important is the experience in shaping our perceptual interpretation? Restored vision. After cataract surgery, blind adults were able to regain sight. These individuals could differentiate figure and ground relationships, yet they had difficulty distinguishing a circle and a triangle. After blind adults regained sight, they were able to recognize distinct features, but were unable to recognize faces. Normal observers also showed difficulty in facial recognition when the lower half of the pictures are changed. Michael May's vision was restored in March of 2000. May has had difficulty recognizing faces of family and friends, as well as emotional expressions on unfamiliar faces. He has also had difficulty in mastering depth perception. For example, he perceives people who walk away from him as shrinking. On the other hand, he does track his own and others' movements with precision. He can play soccer with his sons, and he enjoys movies. He also distinguishes shaded areas from illuminated surfaces. He successfully made the transition from being an expert blind skier using verbal guidance to being a competent sighted skier. May sees learning to see as an exciting challenge, perhaps partly because he's an outgoing, optimistic person with a supportive spouse. Adults who regain sight after being blind for most of all of their lives often experience initial elation followed by emotional distress, depression, and sometimes even suicide. For example, in an Anthropologist on Mars, Oliver Sacks relates that the case of Virgil, who saw little until after having cataract surgery at age 50. Sacks describes Virgil as a mental blind person who could see but could not decipher what was out there. Virgil was often in conflict between looking at objects or touching them, as he had always done, and when feeling visually overwhelmed, he would act as if he were still blind. Virgil quickly fell into depression just 4 months after his surgery and died of pneumonia. Bruce Bauer explains restored vision requires an enormous accommodation from the brain. Imaging studies reveal that primates, as much as 1/4 of the brain, is normally devoted to vision. In blind individuals, these are areas taken on entirely new responsibilities. For example, the visual cortex shows increased activity when blind people use their fingers to read Braille publications. With restored vision, they must be reclaimed. Of the special interest are studies of blind children in India and Canada who, as a result of cataract surgery, regained vision early in life. For example, neuroscientist Pawan Singh describes the case of 10-year-old in Calcutta who had not long after surgery could catch a paper ball thrown to him, recognize drawings of animals, and greet all of his physicians and nurses by name. Sina and his colleagues are tracking the progress of 20 Indian children ages 6 to 15 who grew up sightless before surgical removal of their cataracts. They are surprised by how much kids recognize shortly after their surgery. These findings do not seem entirely consistent with those who studied children elsewhere. Working at McGill University in Canada, psychologist Daphne Maurer has studied young children who have had cataract-induced blindness in only one eye. During infancy, visual information entering the left eye goes mainly to the right hemisphere, while the right eye sends its input mainly to the left eye. Interestingly, those who are blind in only the left eye for the first 2 to 6 months of life lose elements crucial for discerning facial recognition. For example, the ability to detect differences in spacing of eyes. Those of the same age with right eye cataracts do not have this difficulty. It seems that the capacity to notice the spacing of facial features develops only if the right hemisphere receives visual stimulation during the brief and early in life. Kittens raised without exposure to horizontal lines later had difficulty in perceiving horizontal bars. So sensory deprivation can also play a part. Visual adaptation to adjust to artificially displaced field. So we can use prism glasses and our brains will quickly adjust to how they have changed where our visual image sees objects. Let's do that again. So in this first image, what do you see? Now the second image, what do you see? And finally we have the third image. A mental predisposition to perceive one thing and not another is your perceptual set, and what you see in the center of the picture is influenced by the flanking pictures. Other examples of the perceptual set are these pictures here. In the classic version of the nature-nurture debate, the German philosopher Immanuel Kant maintained that knowledge comes from our innate ways of organizing sensory experiences. On the other side, the British philosopher John Locke argued that we learn to perceive the world through our experiences of it. It's now clear that the different aspects of perception depend more or less on nature's endowments and on the experiences that influence what we make our sensation. For many species, infancy is a critical period during which experience must activate the brain's innate visual mechanisms. When cataracts are removed from adults who have been blind from birth, these people remain unable to perceive the world normally. Generally, they can distinguish a figure from ground and perceive colors, but they are unable to recognize shapes, forms, and complete faces. In controlled experiments, infant kittens and monkeys have been reared with severely restricted visual input. When their visual exposure is returned to normal, they too suffer from enduring visual handicaps. The role of personal factors and past experiences in perception can be extended in a discussion of functional blindness, or what Freud would have called hysterical blindness. Electrophysiologist Gretchen von Bommel and psychologist Patrice Rose-Coker of California State University, Long Beach, have identified 150 Cambodian women in Southern California with unexplained vision loss. Doctors and specialists can find no physical explanation, yet it is clear that these women are not faking their reactions to get help or attention. The lack of vision in the women aged from 51 to 70 and ranges from 20 to 100 to no light perception at all. Interviews indicate that all women had lost their vision sometime after the Pol Pot became Prime Minister of Cambodia. Under his communist government, 1975 to 1978, more than 1 million Cambodians were executed or died of starvation. Millions more became slave laborers, suffered severe torture. One Cambodian woman saw Khmer Rouge soldiers tie up their parents, cut their throats, and throw them into a river. Another saw her child bashed to death against a tree. A third watched as her 3 youngest children starved to death. Many were forced to spy on their own families. At times they lived on earthworms, rats, and even the flesh of their own people. In refugee camps, Cambodian women were sexually abused by both the Khmer Rouge and the refugee camp guards. In talking with the women, von Bommel discovered that they had all witnessed some horrible trauma, like seeing their child killed, and then they couldn't see. One victim reported, "My family was killed in 1975, and I cried for 4 years. When I stopped crying, I was blind." Rosie Coker reports, "Our main finding was that the longer the time spent in camps, the worse their psychological condition in terms of blindness. It's almost like a see no evil kind of thing." With a limited funding from the United Cambodian Community, the researchers used a standard group therapy and skill building training to help as many women as would agree to participate in the program. Many of the women were isolated, didn't speak English, and rarely left home, so it was difficult to get them to participate. Mistrust of authority figures also produced a relatively low participation rate. During the Khmer Rouge period, people were told by the army the government needs you would never be seen again. However, of those who came for therapy, 40% showed improvement in their vision. As Myers notes, Michael May's vision was restored in March of 2000. Human perception is remarkably adaptable. Given glasses that shift the world slightly to the left or right, or even turn it upside down, people manage to adapt their movements and, with practice, to move about with ease. Although kittens and monkeys also adapt, chicks cannot. Clear evidence that perception is influenced by our experiences, our learned assumptions and beliefs, as well as by sensory input, comes from many demonstrations of perceptual set, mental predisposition to perceive one thing and not another. Although experienced, we also form concepts or schemas which organize, interpret unfamiliar information, a fact that helps explain why some see monsters, faces, and UFOs, and others do not. Given a stimulus may trigger radically different perceptions. Schemas are concepts that organize and interpret unfamiliar information. Children's schemas represent reality as well as their abilities to represent what they see. Face schemas are accentuated by specific features on the face. Students recognize the caricature of Arnold Schwarzenegger faster than his actual photo. Eyes and mouth play a dominant role in face recognition. Context can radically alter the perception. Is the magician cabinet on the floor or hanging from the ceiling? A given stimulus may trigger radically different perceptions, partly because of our different schemas, but also because of immediate context effect. For example, we discern whether a speaker said morning or die from surrounding words. Human factors psychologists explore how people and machines interact with the physical environments and can be adapted to human behaviors. They help design appliances, machines, and work settings that fit our natural perceptions. Sometimes they use natural mapping to make simple design that reduce frustration in using common appliances. They are mindful of the curse of knowledge, whereby technology developers assume that others share their expertise. A psychologist, their most powerful tool is research. By testing users' responses to alternatives, they seek to increase both human safety and productivity. So our cultural context can also change our perception. Context instilled by culture also alters this perception. For instance, when shown to East African, the woman sitting is balancing a metal box on her head while the family is sitting under a tree. Human factor psychologists design these machines that assist our natural perceptions. The knobs for stove burners on the right are easier to understand than those on the left. Understanding human factors enables us to design equipment to prevent disasters. 2/3 of airline crashes were caused by human error and are largely due to errors of perception. Michael J. Darnell's created a collection of bad human factor designs. Here's a few. A kitchen timer that you can set to time less than 15 minutes unless you first turn the indicator time greater than 15 minutes. The timer doesn't go off initially if you set it for less than 15 minutes. An oatmeal container with a new style lid that looks like a handle. If you grasp the handle to carry the box, the lid flies off and the oatmeal falls on the floor. Two sets of doors within a couple of yards of each other. One set operates by pushing, the other set by pulling. A refrigerator with no handles on the front, you have to hunt for it on the side. Some cars have gas caps on the right, others on the left. One rarely remembers which way to drive into the gas station. Gas caps and trunk lid releases immediately next to each other. To flip the gas tank, you inadvertently open your trunk. A camera designed for children has a button opening the film compartment. It's pushed while part of the film is still unexposed. That is, pictures still being taken on the roll. It ruins the entire roll of film. Darnell notes that usually problem with a device is that it's too difficult to use. In this case, it's too easy. A convenient alternative solution might be having two buttons on the camera that have been pressed simultaneously to open the camera. To combat conditions of monotony, stress, and weightlessness when traveling to Mars, NASA engages human factor psychologists. Is there extrasensory perception without sensory input is called extrasensory perception. A large percentage of scientists do not believe in ESP. Claims are made by parapsychologists for three varieties of extrasensory perception: telepathy, which is mind-to-mind communication; clairvoyance, receiving remote events; and precognition, perceiving future events. Closely linked with these are claims of psychokinesis or mind over matter. Research psychologists remain skeptical because of the facts of so-called psychics have typically turned out to be nothing more than illusions of stage magicians, because of checks of psychic visions have been no more accurate than guesses made by others, and because sheer chance guarantees that some stunning coincidences are sure to occur. An important reason for their skepticism, however, is the absence of reproducible ESP results. In addition, belief in ESP, one must believe in the brain is capable of perceiving without sensory input. So the paranormal phenomena include astrological predictions, psychic healing, communication with the dead, out-of-body experiences, but most relevant are telepathy, clairvoyance, and precognition. Telepathy is mind-to-mind communication, one person sending thoughts and others to receiving them. Clairvoyance is perception of remote events, such as sensing a friend's house is on fire. And precognition is perceiving future events, such as a political leader's death. Can psychics see the future? Can psychics and police aid in locating dead bodies? What about psychic predictions of the famous Nostradamus? The answer to these questions are no. Nostradamus' predictions are retrofitted to the events that took place after his predictions. In an experiment with 28,000 individuals, Wiseman attempted to prove whether or not one can physically influence or predict a coin toss. People were able to correctly influence or predict the coin toss 49.8% of the time. So why do people believe so strongly in ESP, despite any clear empirical support for its existence? First, belief in ESP illustrates our tendency to be easily persuaded by vivid anecdotes and experiences. For example, even when college students have been forewarned about mind reader tricks, they may, after viewing her dazzling performance, be convinced that she is a true clairvoyant. Vivid personal experiences are much more compelling than the abstract statistical data from dozens of laboratory experiments which fail to show the existence of ESP. Second, we are often unaware of factors that influence our thoughts processes, which may lead us to create explanations for our experiences. For example, a husband and wife watching a TV program when one suddenly suggests that they invite certain friends over for dinner. The spouse claims to have been thinking the same thought. Is this mental telepathy? Probably not. It's more likely some stimulus on the TV screen, perhaps the image of an automobile like that of their friends, triggered a common memory. Third, we may fail to recognize chance occurrences for what they are. Deficiencies in our statistical intuitions may lead us to see extraordinary events as almost impossible. For example, what are the odds that at least 2 people in a group of 30 will have the same birthday? Most people grossly underestimate the correct answer. It's actually 7 in 10. Given the billions of events that occur, sheer chance tells us some extraordinary coincidences are certain to occur. Here's one of our favorites. The King James Version of the Bible was completed when William Shakespeare was 46 years old. In Psalm 46, the 46th word is shake, and the 46th word from the end is spear. Even more incredibly is that someone discovered this. The illusion of personal control may also lead us to perceive the phenomena that are really not there. Yale University researchers relied on his tendency in manufacturing a false belief in ESP among their students. Students tried to mentally transmit 5 symbols into other students who guessed what was transmitted. ESP success rate was no better than chance. When the students were drawn into drama by being given a warm-up period before the actual testing began, however, they were confident that the ESP was transpiring more than 50% of the time. Finally, people may believe ESP because they want to. We humans have always had a hard time accepting our finiteness. Believers in ESP proclaim a potential for omniscience, hard time accepting our finiteness, believers in ESP proclaim our potential for omniscience. Some scientists argue that an escape from the humdrum life pseudoscience offers phony mysteries instead of real mysteries, and that it displaces science with science fiction. This completes chapter 6 on perception, and you can review this at any time to help you study for your test.